Similar to the interaction table, Taguchi proposed some typical linear graph for all the orthogonal array. This is one of the examples. This is the linear graph for L8. Actually, two linear graphs for L8. Let me introduce how to understand the linear graph. Here, from this linear graph, we call this a standard linear graph. Actually, linear graph is not unique. You can come up your own linear graph. But here, Taguchi just show you some standard linear graph, so you can use this linear graph to arrange your factors. The purpose is to make sure all the many facts and all the important interactions can be estimated and will not confound with each other. Let's see how to understand this linear graph. It is composed with dot, right? Dot, and also line, this line. Here, the dot or the point stands for the many facts, which means that you need to assign your factors to some of the dot. And what is the line? The line will represent the interaction between these two dots. The interaction between these two dots. So, which means that, as you can see, this is L8. We'll have 7 columns. The number stands for the number of columns, which means that 1, 2, 3, 4, 5, 6, 7. There are 7 columns. If you assign your factors to the dot and make sure that those important interactions, you save the space for all the important interactions in the line. But you need to arrange your factor carefully in such a way the interaction in the line will stand for those important interactions. For those negligible interactions, you don't need to worry about that. And it will not show up in this, linear graph. Okay? It will show up in this linear graph. And these are 2 examples for L8. They have a little bit different. And the linear graph actually is consistent with the interaction table. We use this interaction table to find out the confounding structures. And Taguchi used this interaction table to come up some standard linear graph for you. And these 2 are consistent with each other. What does that mean? Here, if you put factors in 1 and another factors in 2, from this linear graph, it shows you that the interaction between 1 and 2 will happen in column 3. So if the interaction for factor 1, 2 are important, it is better to put it in the linear graph, in the dot of the linear graph. And here, this line will reserve the space column 3 for these 2 interactions. And to prevent you put any factors in column 3. But why interaction 1 and 2 happen in column 3? Let's double check with the table. As you can see this from this table, if we put factors in column 1, another factors in column 2 here, and you can see that the interaction between column 1 and column 2 will happen in column 3, right? These 2 are consistent. How about column 1 and column 4? There's a line and say number 5, which means that the interaction between column 1 and column 4 will happen in column 5. Look at the interaction table again, column 1, and the interaction with column 5 will happen in column 4. So, I'm sorry, 4 right here. the factor is in column 1 and column 4 will happen, the intentional column happen in column 5 right here. So you can see they are consistent with each other. However, in this linear graph, it only saves some line for those interactions which are important. Okay, and this is another linear graph. You can double check with the interaction table, and you still can find out they are consistent to the interaction table, right? Just like 17, sorry, the factor 17 interaction will happen in column 6. And look at the table, 1, factor 1, and factor 7 right here. The interaction will happen in column 6, just like the interaction, linear graph. Any questions? These two standard linear graph is proposed by Taguchi, but you can come up your linear graph from the interaction table, but you need to make sure all the numbers will not be repeated. 1, 2, 3, 4, 5, 6, 7. They cannot repeat it, just like this linear graph. Okay, how do we use this linear graph? First, you need to allocate, you need to assign your factors, right, to the dot. And make sure the important interaction will happen in the line. This linear graph is going to help you how to assign your factors and make sure your interaction can be estimated. First, you need to understand how big your design is. Similar to the number of unknown. If your design, you need to estimate some important interactions, which means that there are more unknown in your model. As I mentioned before, the main effects are some unknown, which is true in the linear adaptive model, right? But if you want to analyze your interactions, interaction will be additional unknown. If you want to analyze additional variable, you need more equations. Similarly, in each arrangement, in each experiment, you can assign the combination of your factors into the model and we'll get one equation, right? Similarly, you can get the equation from interaction where I don't introduce the detail. But the idea is the same. So you need to calculate, we call it how big you need. First, this is called degree of freedom. And I will talk about that later, but basically you understand if you want to analyze the interaction, you need to have a bigger table. In such a way, you can have columns for the main effects, and also you have some columns for those important interactions. How do I use the linear graph? First, you assign your factors to the point. Remember, to the point. And if the interaction is important, then the factors has to be for those important interactions, such as A, B, the factors A and B has to assign to the dots with line connected to each other. Right? Okay. So how do we, there's a suggestion first. There's a suggestion say that if you want to analyze some interaction, you should assign the factors to the point, especially for the factors happen most in the interactions. Let's look at some example. Okay. For instance, this is one of the example. We have two-level factors, similar to the one we just analyzed. Two-level factors, A, B, C, D. And From some theoretical analysis, we already know that there are two important interactions, which is AD, right here, AD, and also BD. The rest of the interaction can be neglected. If you want to analyze in your model, you want to analyze A, B, C, D, and also the interaction AD and BD. How do you arrange? How do you arrange your factors, your four factors? And make sure all the main effects and these two interactions can be estimated. Then we have two linear graphs, right? Because we want to arrange that in L8, we have two linear graphs to select. Let's look at the factors. As I suggest you before, we need to assign the factors which happen in the interaction first. We know A happen in the interaction, D happen in the interaction, and B happen in the interactions. So we need to assign A, D, and B first. Especially D should be assigned first. Since factor D happened twice in the interactions, so we need to find out a linear graph. We need to put D in the dot with line, right? With line. Since if I put D in one of the dot with line, then we can make sure the interaction between D and some other factors can be analyzed. For instance, let's select this first linear graph first. I mean, select first linear graph. And let's assign D, because D happened twice in the interaction, to the dot. Here I select dot number 1. Why I select dot number 1? Because when I select dot D number 1, we know that there will be two lines connected to factor D. Why do I need two lines to connect to factor D? Because AD and BD are important interaction, they need to be analyzed. So once I assign D, next I can assign A or factor B. If I first assign factor A, I can select dot number 2. Why? If I select A in 2, then they will reserve the column 3 for interaction AD. Same thing, I put in factor B in column 4. Because I put B in 4, the interaction between BD can be analyzed in column 5. Since column 5, it will not happen in the dot, which means that I will not assign factors to column 5 or column 3, which makes sure the main effects will not combine with two-way interactions. Okay, so in this arrangement, we can make sure AD interaction and BD interaction will be estimable, can be estimated, because no main effect confound with column 3 and column 5. What's next? A, B, C, D. I already get rid of A, B, D. Now I need to assign factor C. There is only one dot left. Certainly, I assign factor C to column 7. How about the rest of the interactions? Do I need to worry about the interaction between 1 and 7? No, because the problem statement already tell you that the rest of the interaction are negligible. So this is very efficiency. This is very efficient. Make sure that all the main effects and all the important interaction can be estimated without go to resolution 5. If we go to resolution 5, will be great. We make sure all the interactions and all the main effects can be estimated, but the orthogonal array will be very big in this way, since you need to separate all the interactions. As you can see, for two-way interactions of two-level factor is easier. You occupy only one column. But if you are three-level, you need to reserve two columns for each interactions. Then your DOE, your orthogonal array will be very big. Any questions? Any questions for this example to assign your DOE, all right, for 4 two-level factors? And also make sure AD and BD interactions can be estimated. No? Good. Let's double check the confounding structures for this experimental design. We assign, as I mentioned here, right? And we say A in column 2, right? Am I right? Right. Okay, let's double check. We'll put A in column 2, B in column 4, D, C in column 7, D in column 1. And let's try to analyze the confounding structure for this arrangement. And we put it here. From the interaction table, we can have the confounding structure. And this is a confounding structure. What is the design resolution for this design of experiment? What is the design resolution for this design of experiment? 5, 4, 3. Which one? What is the design resolution for our previous example? I heard 4. Any other answers? What is your 4? Yeah, we got 3 students answer. This design is resolution 4. Yes. Recall what is the design resolution for? Many effects will not confound with interactions. However, interaction can confound with each other. Yes. A, B, C, D do not confound with the interaction, but interaction confounds with each other. So it will have resolution 4. Actually, the answer is right here. But design resolution 4 is not big enough to analyze all the main effects and all the interaction, right? But this question tells us that only 2 interaction, AD, only 2 interaction, I put it in red, and BD are important. The rest of the interaction, you see, I put it in green, are all negligible. So you can see only these 2 are important. The rest of the 4 interactions are negligible. Even though these 2 interactions are confounded with each other, the BC is negligible. Therefore, this kind of arrangement still can let us analyze the interaction AD. Same thing for interaction BD. Any questions? This is how we double check our answer from the confounding structure. Okay. And this is the L16 interaction table. White shirts. And you can find a corresponding linear graph for L16. It is bigger. And you can see there are 4 different types of linear graph for L16. And they can you can select this linear graph for different purpose. As you can see in the first one, it looks like a star. Okay, actually it's like a polygon. Have 5 sides. And you can see it has 5 dots. So this linear graph allows you to analyze 5 main effects and also 10 interactions, right? 10 lines. Next, this linear graph will have more dots. It has 7 dots. So this linear graph allows you to analyze 7 main effects and 8 interactions. Not as many lines, but more dots. How about this one? 8 main effects, 7 lines, 7 dots. 7 lines. 8 main effects, 7 lines. They all for 8 main effects. This one, right? This one for 8 main effects, and this one is also for 8 main effects. But they have different structures for the linear graph, which can be applied to different examples. In this way, you can see this one is very special. It has a very dominant factors, and these factors will have interaction for pretty much the rest of the main effects. If your design problem is looked like this way, you should select this linear graph. Here, okay, we have some linear graph. We have some dot can analyze 4 interactions. This one can analyze 2 interactions. So it depends on your problems. You should select a suitable linear graph first, and then assign, as I mentioned, assign the factors happening in the interactions most first, and then assign all the interactions, all the factors in the interactions. After that, you assign those factors that didn't happen in the interactions to any of the dot which is empty. For 3-level factors, a little bit more complicated, but still follow the similar principle. As you can see, for L27, the interaction will always happen in 2 columns. What will be the linear graph? They provide 2 linear graphs. The first linear graph can analyze 1, 2, 3, 4, 5, 6, 7 main effects. Here, the second linear graph can only analyze 5 main effects, only have 5 dots. However, number 2 linear graph can analyze more interactions than the first linear graph. So it depends on your problem style. You should select appropriate linear graph and then assign your factors.